In this example, we're going to take a look at a first-order transient circuit. So in this particular circuit, we have a switch that's been closed essentially since negative infinity, and we are going to open the switch at t equals 0, and we want to determine what is the voltage across the capacitor after the switch is opened. When we approach these kinds of circuits, there are a few things that we want to keep in mind. First of all, remember the formula for a capacitor and for an inductor. For a capacitor, we know that the current as a function of time is related to the voltage and the capacitance in this way here. And similarly, for an inductor, the voltage is related to the inductance and the current using this formula here. Additionally, first-order linear differential equations with constant coefficients are relatively simple to solve. The circuits that we're going to look at here only come in two kinds of forms. First of all, you have a first-order differential equation with the constant coefficient k, in which the equation is equal to 0. And if that's the case, then this is your answer. And A will equal the initial conditions of the circuit. We'll look at that in just a moment. If the equation does not equal 0, if it equals some other constant number, then the answer will take on this form. And A will not be simply solved by using the initial conditions. Well, you will use the initial conditions, but A will not be exactly the initial conditions. Okay, and we'll look at that example perhaps in another problem. Okay, so what are our procedures for solving these kinds of circuits? First, we solve for the initial conditions. Then we flip the switch, look at it and see what's going on, and then redraw the circuit, because the circuit will, in almost all cases, it'll be changed fundamentally. And then this is sort of not a hard rule, but it makes things easier if you apply KVL to networks with inductors or KCL to networks that have a capacitor in them. Okay? And finally, we'll put the equation into a standard form and then solve it using those two standard form solutions that I showed in the previous text. Okay, so let's start by doing our initial conditions. So to draw the initial conditions, or to solve for the initial conditions, we're actually looking in this case for what is the voltage on the capacitor at t equals 0, and previous to t equals 0. Now, keep in mind that you could be asked to solve for a current here, and that would be fine, but the initial conditions for a capacitor would indicate that you want to solve for the voltage across the capacitor. And if it's inductor, you want to solve for the current through the inductor. Okay, so how are we going to solve this? Well, we have to remember two basic things about these new components that we're working with. In a circuit like this, that's been allowed to sit for an infinitely long time, we treat a capacitor as if it's open, an open circuit. And I tend to remember this because, well, if you look at the capacitor symbol, it's not actually touching, so it kind of looks like it's open. And the inductor will work the opposite way. You'll treat it as a short. Okay, so because this circuit is open, we can say essentially that this entire branch of the circuit here has no current flowing through it, which means that the battery at this point in time has is providing a current only to this side of the network. Okay? And based on that, we can then solve for Vc of t. Vc of t is going to be the voltage from this point here to this point here. So I would just simply use voltage division. We can use voltage division to find the voltage here. And then once we have the voltage there, we can combine it with the 6-volt source and solve for Vc of t. So we'll use voltage division. And that will tell us that V at the 4K resistor is equal to 6 volts that are provided times 4 over the sum of the resistances, 4K plus 9K plus 3K. All the K's are going to cancel, of course. And we'll get 24 over 16, and that's going to give us 3/2 of a volt. Okay. Now to solve for Vc at 0, what we'll do is we'll do a very simple KVL equation. So by applying KVL, we get minus 6 volts plus 3/2 plus Vc at 0. And that equals 0. Okay, assuming, of course, that I've labeled my polarities in that way. So when you solve for this, you'll get Vc at 0 equals 9/2 or 4.5 volts. This is our initial conditions. Okay, so now what we want to do is we want to solve the circuit once the switch is open. So when we open the switch, let's take a look at that. When we open the switch, this whole area becomes open. And when it becomes open, what does the battery do to the circuit? It does nothing. This whole entire branch is dead. It supplies no current to the circuit. And so our effective circuit now becomes just this outer loop. So we can redraw the circuit. And when you do that, the circuit will look like this. Okay? And now that we've redrawn the circuit, we can solve for Vc of t. To solve for Vc of t, remember that earlier I mentioned that it's easiest to apply KCL to a first-order circuit that has a capacitor in it. So what we'll do is we'll choose this as our node, and we'll choose our currents going this way. We can really choose them any way we want, but this just makes things easier. And now we'll solve our KCL equation. Okay, so right here, we're using C dVct dt. And then here we'll be using VCT, because that's the only thing supplying a voltage, right? Times or I'm sorry, divided by our resistance. So to kind of get this sort of looking a little bit closer, I'm going to pull the resistance out. Remember, it's V over R, so I'm just going to say 1 over R. And that's 9 plus 3 is 12, times V CT. Okay, and that's a KCL equation, so that equals 0. Okay, now let's start plugging in some values. It's easiest when you're dealing with these capacitors to try and write them in terms of whatever whatever term you're using for the resistors. For instance, these are in kiloohms, so I'm going to try and rewrite the microfarad in terms of kilofarads. So to do that, I can simply just say that 1 microfarad is equal to 0.1 millifarads. And 0.1 millifarads is the same as 0.1 over K. Okay, so I'm going to rewrite this in for C. So I get 0.1 over K dV CT dt plus 1 over 12K VCT equals 0. Now the important thing about actually solving this and putting it into a solution that gives you the final voltage is that we need it to be in standard form so that we can apply our simplification to this. Okay, so what I'm going to do is multiply through by K over 0.1, and that'll cancel this out. So we get d VCT dt plus K over 0.1 times 12 K VCT. And the K's cancel. And what we are left with for our standard form equation is dVCT dt plus 1 over 1.2 VCT equals 0. Okay? That's our standard form. And now we can solve for the final differential equation. Remember that the differential equation is telling us what does this equal right here. Okay? And remember that when we have a standard form differential equation where the value equals 0, that our answer is going to be oops. I guess I drew on the wrong layer. It's a little hard to look at. So I'll just tell you what it is again. Remember, it is it's going to be VC of t equals a e to the negative kt. And A is our initial conditions. We solve for our initial conditions, and that was 4.5. So VC of t equals 4.5 E. And then K is that constant that we got in front of our term here. And so we'll just rewrite this as negative t over 1.2. And that's the solution to that problem.